Welcome to Homework Lib.
Okay, so according to Kirchhoff's law, we have EMF minus IR minus IRL, and then minus L di dt is equal to 0. R is the resistance on resistor. RL is the resistance on inductor. Okay, and we know L is the inductance of an inductor, and EMF is the source voltage. So if we do some arrangement here, we have epsilon minus I times R plus RL is equal to L times di over dt. And then we can put negative sign on each side. This will give us I times R plus RL minus EMF, and then is equal to negative L times di over dt. So which will have I minus EMF over R plus RL is equal to negative L over R plus RL times di dt, because I divided by R plus RL on each side. Okay, so eventually we'll have di over I minus EMF over R plus RL is equal to negative R plus RL over L times dt. So therefore, we can put the integral here. Okay. So eventually, we'll have I is equal to epsilon over R plus RL times 1 minus e to the power of negative R. Ooh, I need to put a parenthesis here. Negative R plus RL over L times t. So we know VL can move to IRL plus L times di dt. So we do some arrangement here. Eventually, we'll have VL is equal to EMF over R plus RL times RL plus R times e to the power of negative R plus RL over L times t. So for the next question, the potential across the source voltage, which is the potential across EMF, should be 50 volts, since initially there's no currents on the resistor. So therefore, all the potential was on the inductance, and the potential on the inductors is equal to the potential of the source, which is 50 voltage. Okay. For question C, well, we know when time becomes infinity, the potential across inductor is 20 volts, which is VL equals 20 volt here. So therefore, the potential across the resistor should be equal to EMF minus VL, since it's a series circuit. Okay, and we know the potential across the source is 50 volts, and we know VL is 20 volts. So therefore, we have VR is equal to 30 volts. And we know the currents in the circuits is actually equal to currents through the resistor. Okay, so therefore we can determine the currents by simply use VR over R, which is equal to 30 volts over 10 ohm. And this will give us 3.0 ampere. So the currents in the circuits is 3.0 ampere. And for question D, well, when the t becomes infinity, VL is 20 volts. So therefore the resistance on the inductor should be equal to VL over I, which is 20 volts over 3 ampere. And this will give us 6.67 ohm for the resistance on the inductor. And for the last question, we know the time constant tau here can be equal to L over R plus RL. And we know 1 over tau times t should be equal to 1. So therefore, R plus RL over L times t is equal to 1. And we know VL is equal to EMF over R plus RL times RL plus R times E, and then to the power of negative R plus RL times T over L. So this will give us VL is equal to EMF over R plus RL times RL plus R times E to the power of negative 1, since R plus RL over L times T is equal to 1. Then we can substitute back to the equation here. And that's how we get this equation here. So therefore, we can plug in the values to determine the voltage across the inductor, which is 50 volt over 10 ohm plus 6.67 ohm, and then times 6.67 ohm plus 10 ohm times e to the power -1. This will give us VL is equal to 31 voltage. So if you take a look at the graph, when VL is equal to 31 voltage, the time is equal to 2.4 millisecond, which means that the time constant is equal to 2.4 millisecond. So therefore, we can determine the inductance, which will have L is equal to tau times R plus RL. If we plug in the values, we'll have 2.4 millisecond times 10 ohm plus 6.67 ohm, and this will give us the inductance is equal to 40 millihenry. And these are the answers for this question.